In my last lecture, I discussed the idea of how machines work, specifically that the work that you put into a machine, such as a lever, is equal to the work that you get out of a machine. So to move 100 pounds 1 inch is the same as to move 1 pound 100 inches, for example. This is the idea that underlies any kind of machine that you use. Now, how is Pascal going to use this idea in order to understand the equilibrium of fluids? Well, let's think about it in this way. So let's imagine that we have a chamber that has two openings. This is going to look a little bit different than the chamber that Pascal had been considering so far, but you'll see why I'm doing this in a minute. So let's suppose this chamber has two openings, one that is on the left side. It has a very large cross-sectional area. Okay, so this is kind of a tube coming out of this chamber on this side, and another tube that's coming out of this chamber on this side, and there's a piston on each side. Okay, and let's suppose this tube has a diameter so that the cross-sectional area is A, and this tube coming out on this side has a diameter such that that has a different cross-sectional area A. Let's call that the area on the output side, and we'll call this the area on the input side. And again, one has to imagine that this entire region is filled with a chamber full of water, let's say. Okay? And what's the idea here is that this chamber of water, I'll tell you where I'm going with this, this chamber of water acts as a machine that multiplies forces. This is what we are getting. This is what we're going to get to. So in a similar way as, so kind of as a reminder, if you have a lever like this, if you apply a force on this side, we'll call that the force in, you get an output force on this side, and that output force can be much larger than the input force because the way that the lever is configured. So similarly, we're going to imagine that you apply an input force on this side, and that is going to allow this chamber full of water to exert an output force on this side. And the question is, what is the ratio of the output force to the input force? If the output force is exactly equal to the input force, then this really doesn't multiply or increase the forces at all. It doesn't give you any mechanical advantage. But if, for example, you can with a small input force get a large output force, that is, that ratio is maybe 2 to 1 or 3 to 1 or 100 to 1, then this is going to act as a machine that multiplies forces. So how do we figure out whether or not this does multiply forces or not? Well, so how do we figure out what this ratio is? Well, a strategy for figuring this out is going to be to use this idea that the work you put in is equal to the work you get out, right? This is the way that we analyze this lever. This is the same way that we are going to analyze this fluid-filled chamber. Well, what is the work you put in? Well, that is the force that you apply on the input side times the distance that that piston moves on the input side. So there's going to be some distance that this piston moves on the input side, and that has to be equal to the force that is exerted on the output side times the distance that the piston on the output side moves. So I know I'm drawing several arrows here. I'm trying to draw this in as simple of a way as possible, but you'll have to keep in mind I'm trying to label these. So this area represents, this arrow represents the force on the output side. This arrow represents the distance that the output piston moves. Okay, so if we want to find out what the ratio of the output force is to the input force, then by rearranging this formula, you can see it's going to be in the same ratio as the distance that the input piston moves compared to the distance that the output piston moves, right? So if we can find this ratio of how far that moves compared to how far that moves, we will be able to figure out the ratio of the output to the input force, and hence we'll find out what the mechanical advantage is. So our question has really reduced to the question of what's the ratio of the input distance to the output distance. So what is the distance that the input piston moves compared to the distance that the output piston moves? So if we can answer that question, we'll have solved this problem. Well, how do we figure that out? Well, we have to think a little bit about how fluids behave. And if you think about this piston, let's imagine that this piston moves by some distance. Let's say it moves from here to here. So if the input piston moves, the input piston moves a distance d in, then it will displace a certain volume of fluid. It will move or displace a certain volume of fluid, right? A volume of fluid. And how much volume of fluid does it displace? Well, if this is a cylinder and it has some cross-sectional area A in, it moves some distance d in, the volume that is going to displace is the area of the input piston times the distance that the input piston moves. So that's kind of the volume displaced on the input side. So you can imagine like this, if it moves some distance from there to there, it's going to displace all this volume of fluid, right? What that means is it pushes forward, that fluid is going to flow into here, and it's going to increase the volume of fluid in here, but fluid can't just sort of get compressed and go away. It's going to have to move this piston outward. So the piston on the right-hand side, on the right, moves by an amount so that that volume is conserved by a distance required by the conservation of volume, by conservation of fluid volume. The fluid doesn't go away. Whatever fluid is pushed out on the right-hand side has to be pushed out whatever fluid is pushed on the input side has to appear being pushed out on the output side. So in other words, the volume on the output side has to be equal to the volume on the input side. Or in other words, the area of the input piston times the distance that the input piston moves has to be equal to the area on the output side times the distance on the output side, right? So this volume, so if this one moves, it's going to move a smaller distance, of course, because it's got a larger area. So this volume right here has to be equal to that volume right here. That's going to give us a way of calculating how far the output side moves. So in other words, this is going to allow us to find the ratio d in over d out. It's going to be the same as A out over A in, right? So this formula that we've developed right here strictly follows from the idea that the amount of volume that, I guess, disappears on the input side has to appear on the output side. And now we can take this and plug it in up here to find the ratio of the output force, force out to force in, is going to be equal to, well, d in over d out, which is A out over A in. And here, then, is a formula for the mechanical advantage of this fluid-filled chamber with two holes in it. I'll put two boxes around this to emphasize it. This is Pascal's principle. So I don't know if I can slide this up a little bit. So this is called Pascal's principle. Pascal's principle, finally, we've come to it. Principle. And it is a principle that describes when we have a fluid-filled chamber, the mechanical advantage that we get when we have a small hole on one side and a large hole on the other side. So for example, if the area on the output side is 10 square inches and the area on the input side is 1 square inch, then the mechanical advantage is a 10-to-1 ratio. So if we push in with a force of 1 pound on a 1 square inch piston, we get an output force of 10 pounds on a 10 square inch piston. This is Pascal's principle. This is the basis for all of how hydraulics work and how a jack works, for example, a hydraulic jack for a car. So let's pause there. When we come back, we'll talk a little bit more about some examples of how this works. Thank you.